Thank you for tuning in today. So today I'd like to introduce our research on this technology and the society's mobilities and various accessibility for the vulnerable users, VRU, in the socio-technical systems with advanced transportation. So I'm gonna see. Here I have to use the mic. Can you do for us introduce these teams, and can you do some introduction words for us?
Yes, certainly.
Okay.
And welcome. All of my stuff was on my computer. I apologize, my welcome speech, but thank you for attending this webinar for the Center for Advanced Transportation Mobility. I am Dr. McBride. I am the director of the center, which is housed at or led by North Carolina A&T University. I want to thank you for attending this second seminar or webinar. And we have two of our researchers who are working on projects within our, well, the focus of our center is on the research priority area, improving mobility of people and goods. So Dr. Seong and Yi, they are both working on a project that is related to one of our key areas, which is vulnerable road users. And so the particular project that they are working on is led by Virginia Tech Transportation Institute, but they have certain components that they are working on and will report on some of their findings as they have been going through this research project. Again, I want to thank you and welcome you, and I will turn it over to Dr. Seong and Yi.
Yes, thank you, Dr. McBride. Let's get started. I'm here with Dr. Seong, so as Dr. McBride introduced, and with two great students here at A&T, the Debbie and the Kelvin. And before I start, I want to highlight that this research has been done with the Virginia Tech team, the VTTI, Dr. Justin Owen and Andrew Miller, and they're the great students. They're VTTI from the computer science, and they are working on the different topics, routing and crowdsourcing and iOS development. But today, I want to focus on the research work that's done here at the A&T, so mostly the computer vision and the AR and the social impact of this development. And mobility is very important for everybody, but specifically is fundamental to active aging of the senior citizen and linked to the health status and the quality of life. So if there's those applies. And dependent on the walking and the wheelchairing on sidewalk, because many of them voluntarily give up the driving, and they can no longer drive. According to the CDC survey, the pedestrians aged over the 65 accounted for 20% of these deaths and 10% of the injuries, total of 30%. That is higher than the composition of their population, which is 13%. So the pedestrian safety for this elderly person is a growing concern these days. So we decided to develop some aging tool for them, but in developing, so we have to consider many factors. So one of the key factors we are considering is vision deficiencies, such as macular degeneration and cataract, and glaucoma, diabetic retinopathy, and retinitis, and pigmentosa like that. And in addition to those diseases, we have to also consider the reading disorders such as dyslexia. Also, we have to also consider these perceptual and the cognitive problems, and especially when there are many information on the road, so there should be some difficulty in the separating the key important from this unimportant information. So in this, for these regions, we have worked on these issues, important issues for pedestrians on this sidewalk with the mobility impairment, rather than this car navigation. So computer vision can be used to have these the VRUs to aid these elderly mobile users with the mobilities and independence. So enhance the mobilities and independence. So to understand these visual worlds using the visual images from the camera of the mobile devices, and we have used AI, the artificial intelligence. So artificial intelligence is not new these days. It's being used here and there, but especially the deep learning. Deep learning is one of the type of the AI. AI includes the deep learning and the shallow learning and many others, but we have focused on this deep learning to contribute to the computer vision development, especially the focus on this image segmentation and object detection and the facial recognition and edge detection, etc. So we will explain one by one on this topic, how we have used. So this is the overall steps we have taken so far, and considering all these prior knowledge and the feature and the images related to the traffic sign and the traffic signal information and the transportation. And using these prior knowledges, we train these algorithms and the systems and develop these algorithms in this mobile device, especially for this object detection and the classification and the location of them, and classify and deliver the key information to mobile users. Also, we have to consider these wheelchairs on the sidewalk and the condition of the sidewalk and how they are driving the wheelchair on the sidewalk. So we also added this sidewalk tracking system with a departure warning. So in developing this app system again, so we have tried to use the sensors already built in the mobile devices instead of adding more sensors. These days, more sensors, new sensors are coming on. But if we have to add these new sensors to the system, then we have to pay. It's not free. And we also have to consider the space and the computational load and the wiring. So there are a lot of limitations. So that is why we decide to use the sensors already built in this app. You know, or you may not know, all these sensors are already on these most mobile devices, like accelerometer and the gyroscope and compass, GPS, and the light sensor and the barometers. And those sensors for the motion measurement and the GPS and the magnetometers are for the positioning. And these days, I think you have seen this new ad from the Apple or some Samsung. They are starting to use the LiDAR. There is a distance sense for this AR function, the augmented reality function. So they have more of the speed using the 5G or 6G and more of the computational capabilities than AR is coming through. Of course, in developing this mobile app, the computer vision is not only features, only functions. We have to consider the capabilities of each mobile user and the weather condition, traffic, and accessibility, considering the road shape and road conditions. And for other features, the free GTI, the research team is working on, and we have worked on these other stuff like machine vision and AR and the social impact. So we are combining all these ones to make a decent mobile app for VR use. And as you expect, we are not only teams working on these important problems. Some other apps are available already, like the video call, real-time assistance, and the speech-to-text mobile app, and tell the location of the parking space, especially for the disabled person, and the bathroom location, and to tell what is the street addresses nearby to help them to navigate. And this is an existing app, and more than that, there are some advanced stuff in the literature survey, the papers, and those are the authors, and they provide, they have developed a function on this station information and obstacle avoidance. Of course, they use the machine vision and the navigation stuff. And more about the aiding the food containers and what is the street sign and the colors helping and where is the crosswalk and how and when we can cross this crosswalk of course, with indoor navigation, because houses are their major places to live and to many things, tasks. Again, so we have used this artificial intelligence, and because it used a neural network to train these algorithms and the systems. Without this, we don't have to program everything one by one. So using the neural network, as we are learning some stuff from the environment, then we can make this system learn by itself. And it is so prevalent these days without knowing that we are already using this AI by searching the Google and by using the Facebook and Apple Photo applications. And for myself, I'm using for different reasons. First of all, this computer vision, and the second is the control of this ground robots and the ground vehicle and the area vehicle and the robot manipulators. So control, very smart control, they adapt itself and tune itself with this unexpected environmental factor disturbances. And for this research, we have used the TensorFlow. It's a very nice the software, and it's an open end-to-end source platform. And we have used this software for training and running neural network for classification and image recognition. So there are several the neural networks we have used, and one of them is a faster region-based convolutional neural network, so-called ICNN. This is a relatively new method. It's introduced about 5 years ago or 4 years ago, 2015 or 16. And after taking this video from the camera, then it uses the convolutional layers to extract this feature in the map. Then there are two paths, and one path is going through this regional proportional network to get this location of this feature. And later they combine these two features from this each loop. Then on one screen, it shows what is the feature with the classifier and what is the exact location with the bounding boxes. That is the first method. And the second method is so-called SSD, the single shot multi-box detector. So instead of using these two paths, this SSD uses a single forward path and combining this bounding box and the classification. But compared to this previous method, it used a very simple convolution, the filter, to reduce the computational load. So when you compare this first method and the second method, of course, this second method, we have to lose some accuracy. So it's very fast. So more proper when you use these mobile devices. These the chip, the microcontrollers in your chip is getting more and more fast. But so far, there are some difficulties in implementing these the full faster ICNN on this mobile app. So that is why we select to use this SSD. So there is a quick comparison this SSD here and the faster ICNN. The SSD is faster than the faster ICNN. It sounds too weird, but it's faster than this faster ICNN. And but it's very good for this memory, the limited memory, and this computational capacity of the mobile devices. So there is a quick result on this sign of detour and traffic information. In the simultaneously, if you imagine you are on this wheelchair on the road, then you have to check this upside. There's a traffic sign and the traffic signal. And simultaneously, you have to check this road condition. So while checking, there's a lot of information over there, so you may miss this uneven or the broken or end of the sidewalk and the deviation from the center. Then you can go to this graph. So we don't want that. So if we put this together, then the mobile users on the wheelchair can check these two information simultaneously. So this is a quick simulation on the sidewalk in front of the A&T engineering building. Then just very small picture is showing this what is the traffic signs on the road and tell these mobile users the wireless communication. there are a lot of communication ways. So one of the ways is using this text, what we will introduce later. They can use the voice or some other gesture or augmented reality. And it's not end. So we have to consider one more thing. So there are a lot, as you drive on the road, you have seen this, the stop sign behind this tree or some obstacle and on these trees and the bushes and the leaves, sometimes on dirt. So it's not clear what is the sign. In other words, it is a heavily occluded object if it is on the road. Then in this case, we have to add one more of the function, that is instance segmentation. So compare these two, and it shows this location with these bounding boxes. But if this is uploaded, then it's not possible to accurately detect what is the object. Then this instance segmentation just shows this boundary and the map. And with this map, then we can tell more accurately what is the sign and what was the information on the road, even if it is behind this obstacle. So we call this a mask RCNN. That is a combination of the RCNN I introduced earlier in this presentation with mask stuff. But as I explained before, this RCNN is very heavy, computationally heavy. And we just combine this mask with SSD, this single word path neural network. Then you can make a system process faster and put this mask on this and this. So in this mask SSD, each pixel belongs to this each object. So this is the implementation of this the mask SSD on the detour sign. So even if some of the information is blinded like this, then you can successfully tell the wide sign. And for this transportation, the method, even if it is not showing the full images, by this segmentation here and here, we can detect what is it. And this, because there's some problems, as you know, the COVID-19, we cannot go on this street to check these algorithms. So there is some implementation indoor, the lab space. This is an engineering building, and it is showing the 3D-dimensional. We use a 2D camera, and you can see this clearly the boundary of the object of interest and what is this. So next is the implementation on this mobile device. So there is a good tool, so-called the TensorFlow Lite. Then using this the software we can implement on this Android app and the Apple performance. So the ideal case is we can train and implement on the devices simultaneously on these mobile devices. But as you know, the machine learning is not easy to process in the mobile devices for the reasons I mentioned several times. So our strategy is to train these algorithms offline, that is using this GPU and the CPU, high functional GPU, CPU, and sometimes we use a cloud computational the software, and after developing this one and implement on these devices. So there is a quick check of this app, and there is a Galaxy Pad. Then click this button, then it shows this stop sign and other types of the stop sign, and the more signs coming up of the detour. And it's showing this what is what type of this, and is the condition of the sidewalk. And we tested on the field. She is the baby, checking this sign on the street, and different angle and different distances. This is blurred because of the sunshine, so it's not easy to see. So we tested again indoor for you to see the screen, checking this traffic sign using the mobile app that we have developed here and put in mobile devices. And after classifying and detecting this object, we have to tell the mobile users what is the information the users have to know. And one of the way is the voice recognition, because sometimes they miss some information on the screen. So instead of this keep watching the screen, if we use this voice, the function, then we can tell even if this one is not watching on the screen. And this is a little bit futuristic research. And the other way is using the gesture and vision impairment or this hearing impairment, and they may have some difficulty in communicating with mobile devices. And while they are handling this wheelchair on the sidewalk. So in this case, the gesture recognition can be one possibility. It is playing a little bit faster, but the point is it is recognizing the motion of this hand and is communicating with the devices, the exact angle she moved. She is a Batu, one of our undergraduate students. So she developed this gesture recognition and connect with some specific devices, this motor. So later, we're gonna put this gesture recognition on the mobile devices for this communication, for easy communication. And I said the other features we want to introduce is the sidewalk detecting using the hue transform. There is some transform of the line. If you see in the screen, then the change this information because this image has a very big the data. So just select the angle and the length, then send the information for the image detection and the sidewalk detection using the comma filter. So if you are on the wheelchair, the screen shows what is the line on the left and the line on the right. And this graph, you can see this graph and showing in the middle, it's showing this how far do you deviate from the center of the sidewalk. So if you are doing something else on the wheelchairs, if you are deviated from the center of this sidewalk, that means it's not safe, then give the warning sign to the user. So this is how much you deviated. So this hue transform is very good for these straight lines. But sometimes the line is not straight. Then instead of using this hue transform, then we can use the polynomial approximation. And this video is done by my other student, Ellen. And we just tested on the ground using this curve and this fifth order or third order polynomial, and this dashed line shows the center of this lane. Then the 100% that is a very the right, and the 0% very left. So it shows is how much the 50% is ideal. It means you are in the middle, but the 100% is very bad as you're departing the lane. And the last features, augmented realities, will be detailed by Dr. Seong later today in this presentation. But I just quickly touched these augmented realities for better communication with the mobile users, wheelchairs, and these persons. Then showing this information on the same screen, the real time with the texture, the information, some other stuff. Of course, in the labs, we are using these Oculus, but these smart glasses, Google glasses, are coming to commercialize. Then we can combine later for this, the implementation of this AR stuff. And it is showing this, again, this AR feature in the lab space. And here is Kelsey, the student, that's the student in the MA department, using the camera and scanning this space. Then after scanning this space, you can put in the file. Then on this Oculus, you can select the space you want to go. So now here is selecting this space you want to go. Then on this Oculus, then you can check this what is the space, and he is seeing himself there. So this panoramic camera is getting on this mobile devices. We are preparing this new features and put this the machine vision with AR on this mobile app. And I said earlier in this presentation that Apple and the Samsung is bringing the LiDAR. LiDAR is a distance the sensor. Then when you have this distance data on the app, then one good thing is you can check this how far from the obstacle and when is the way in case you miss. So if you are very careful, you can see these all the things, but from this wheelchair is a very limited side of view. Then you may miss some these obstacle on the road and the crack uneven and where to go. So we tested in-house. This is the house of the method sponge, the LN, and he is scanning all this environment. Then the warning sign if it's close the obstacle and show the direction on the AR. So this full LiDAR is not on the mobile devices, but I said it is getting coming true, and already some these the mobile devices have already this LiDAR. So we can put this LiDAR stuff for this distance and obstacle, the checking and moving this obstacle and the static obstacle. So for this machine vision, we have tried to find a solution to aid the elderly person or some impaired person by detecting the stuff in the real time they recognize and send the key information to the mobile users like a signboard and obstacle with the sidewalk information. And the more detailed information of this machine vision is available on this the publication and some more of the presentation stuff. And next is about the interactive mobile-based transportation aid for VRUs, and Dr. Seong will take the stage and give the detailed information about this research.
Yeah, hello. This is Yeohno Seong. This is the part that I'll be presenting to you guys about. Very much developing mobile-based transportation aids for VRUs. So let's get started. So I think you just heard a very wonderful presentation looking at very technical aspects to support our vulnerable road user population, basically to overcome vision, cognitive, perceptual problems. We approach these problems from machine learning, deep learning, computer vision, object detection, image segmentation, and virtual reality. Very technical. I will try to keep our feet in the technical area a little more longer, but we'll try to shift our focus on more socio-technical systems in which technology and society can receive a balanced attention to identify challenging problems. Although we are all involved in these studies, I am particularly leading a couple of studies. First, one developing interactive mobile-based transportation aids for our target population, VRUs, and the second being more focused on the social aspect of technology-oriented transportation system, especially when more advanced autonomous vehicles are introduced to the society. Something like at the SAE level 3 or more, conditional, high, and full automation. So let's get started. I might not have to lay out the foundation of our studies, but to refresh our clearly lay some background, let me say some few words about what particular mode of transportation and the target population, which is VRUs. There are several means by which people move from one place to another. The means by which people move around is what we term as the modes of transportation. These include public paratransit, private, and the last one we all are familiar, transportation network companies, TNCs, most venture companies like Uber, Lyft, among others. All these modes of transportation serve different classes of people. We have the young, mature people, children, aged, and the disabled. But in the study, our main concentration is on disabled persons and older adults. So the question is how to modify these modes of transportation to suit these people in the society. These are some of the examples that are used to service this minority group in the society. The disabled and elderly are unable to use public transportation, and they usually offer paratransit, making it the most widely patronized service for this group. One question being asked by most researchers is, how do we cater for transportation needs of the disabled and elderly in the society? There's a school of thought which talk about whether to modify the existing modes of transportation to suit them or find a specialized mode for them. But the decision of all these is financially driven a lot. 20-some years ago, after passage of the American Disability Act, transportation choices for people with disabilities are still limited. There are persistent gaps in compliances that continue to create significant barriers for people with disabilities. Few transportation options exist for people with disabilities where no public transportation is available. Further, the demand for paratransit continues to proliferate in the United States as a result of its aging population. The existing paratransit models cannot afford to meet the increasing demand of this aging group. Paratransit is an alternative mode of transportation, most often provided by minibuses, which provides door-to-door or last-mile shared rides upon request by eligible users. This mode of transportation is particularly valuable because it is not based on the fixed route. Paratransit use has soared in the past 20 years, along with its cost. However, users in many cities experience significant problems with their paratransit system, including problems with the service quality, service being very tardy or sometimes halt without any notification at all, sometimes just caused by capacity limitations. Adding more pains to the problem is the necessity of the plan ahead or pre-arrangement. Same-day paratransit trips are unavailable. It has to be some day advanced, which means that any activities not scheduled ahead or mildly emergent activities are beyond the reach for these populations. The passengers are given 30-minute window. If failed to meet, they will be marked as no-show, along with the penalties and other disadvantages for future reservations. So this problem becomes exacerbated in suburban or rural cities, which the carbon footprint is more prevalent due to the lack of public transportation. So what will be the current process right now? This is the current structure most riders go through. First, to schedule the ride through phone calls or web-based system in some cities. The companies dispatch the service on the day riders get picked up and may pick up more passengers, which the passengers do not know in advance, which means that the riders have to factor that into their own scheduling without knowing how long it will take, and finally deliver them to the destination, obviously. But they mostly experience slow service en route, that is a long waiting time, and sometimes have no idea of when the ride will be arriving or how long it will take the service to get to the destination. So basically much different and variable time to time. Therefore, in response to these challenges, we are very much interested in making their lives to get by through daily and essential activities. So in this generation of smart devices, handheld devices feel perfect match for our interests. So we decided to go for an Android mobile application to help these vulnerable users. to navigate to do certainly their parts, planning trips, making reservations, tracking the availability and the location of their paratransit in real time so that they can be present at the place they want, at the time that they want it efficiently and effectively. So the Android, you already show some part of the apps already before. So Android allows us to have strong code editing environment to develop the creative user interface, as you can see here. But we may need to pay more attention to the ecology in which the device can be used. During the reservation phase, the users may be in some comfortable settings like their homes. But when they are trying to get picked up, they might be pushing themselves in wheelchairs, walking with canes or walkers on busy streets filled with loud noises. So we thought that we may have to first sacrifice some functionalities instead of implementing rich features. Androids help us to build the front-end interface of the app. So it is usually in Java and Kotlin programming languages. For the back end of the system, we use Google Cloud, providing good computing resources to build, deploy, and scale applications, websites, and the services. Google Cloud helps in building the back-end server for the application. The Firebase real-time database is a cloud-hosted database, and the data is basically stored as JSON, JavaScript object notation. This is very lightweight data interchange format and gets synchronized in real time to every connected client. So this is very easy to read and write for humans, and this is easy for machines to parse and generate. So when we build cross-platform application with our iOS, Android, and JavaScript SDKs, all of our clients share one real-time database instance and automatically receive updates with the newest data. Additional benefit is that these are universal the data structures. Virtually all modern programming languages support them in one form or another. So it makes sense that the data format that is interchangeable with programming languages also be based on these structures. So we have been developing two apps, one for drivers and the other for riders. For the driver, traffic information along with the rider's location would be critical. For navigation purpose, the driver would need to know the rider's destination or destinations for the multiple riders. If there are multiple riders, it makes the problem far more complicated. It becomes the TSP, traveling salesman problem, minimizing the traveling and the distance to visit multiple places. User apps have several functions, not much showing on this presentation, but including dial buttons for reservation, predicting local transit, bus time in case the rider wants to ride a public transit, and the map interface, which shows available buses online and things of that nature. Buses have different colors and number tags, which help riders to know the bus they are riding. Additionally, for the users app, we focused on helping them track these paratransits to reduce their cognitive burden of not knowing when these buses are arriving. That is, it provides a customizable tracking map, accessible information to users of paratransit transportation for usually physical mobility impaired or have cognitive impaired. We also thought the use of augmented reality could be very useful. You saw that a couple slides in the previous presentation by Dr. Lee. Current technology of augmented reality is very advanced, and its versatility virtually has no limit in applications, including one of the most famous applications, Pokemon Go, that you see in this picture. The game that fascinated a lot of people into augmented reality. Some of more examples, including football games, broadcasters, IKEA places, flight pilots, even neurosurgeons to support it in the surgery. One of the best examples for AR is navigation, as you can imagine. Considering the target population, particularly AR technology would be very useful to ease users' physical and cognitive impairment. The app was built using Android Studio, AR core software development kit, and the Google Maps application programming interfaces, APIs like Street Views API, Directions API, Google Play Services API, etc. AR Core is a good software development kit, SDK, Google's platform for building augmented reality experiences. It uses concurrent odometry and mapping COM to track the surrounding in AR. Using different APIs, AR Core enables our phone to sense its environment, understand the world, and interact with the information. You already saw this the slides before, but let me just briefly say a little bit about it. Smartphones also have many components that are very useful for our web development, including all these sensors. Here is a short demonstration of the app. Play that video. Okay. For demonstration purpose, if the user just collects the destination, it automatically calculates the shortest route and then uses the phone's camera on the rear to identify where you are, superimposing directions and the details on the display rather than just presenting you with a map. It also shows your road names and the distance in augmented reality, as well as major turnings to keep you heading the right way. I will just let you watch a little bit more video. We can move on, I guess. Okay, we have some other important functions. Some are already done, while others we still plan to build very soon, including multi-language support for ethical diversity. According to the Metropolitan Transit Authority paratransit operations briefing in 2016, 21% of the United States population speaks a language other than English at home. Real-time weather information is something more that we are putting in. We already put that in to help riders to know the weather of the places to help them plan their trip. The next work that I would like to talk about is consideration of technology in the society simultaneously. This is a project that we have funded a couple years ago, led by one of the leading investigator is Dr. Lee. Dr. Yi. 9 universities were selected for this competition. The project our work is based on is GM supported, given bare minimum vault turning into autonomous vehicle in 3 years. This is the 3rd year which we are supposed to meet all together to compete against each other. I think because of the COVID, the schedule was delayed a little bit. So Dr. Sani is the one of the leading investigator on this project. In year 2, we were placed in the 2nd place overall. Of the static group, I'm leading the group called the social responsibility, looking at almost everything except the technology directly. But we still need to consider the technology because our purpose is to identify the impact of technology on humans and society, then reflect it back to the cyclical feedback to modify the design. Let me give you just a short example of very actual testimony that we have received in 2019. This person was hired by the State University in Michigan. He relies on Uber for every transportation needs because he is legally blind. He said feeling somewhat fortunate that he was given 3 months reimbursement-based assistance from the university, which most do not have this opportunity. Still, it is not easy to maneuver around. The problem becomes much worse due to much better but not so accurate GPS drop-off point and his familiar spot or meet-up places with someone. Suddenly he got lost. How can we design the system so that this person can find the location to meet whoever the person that he wants to meet? Let me just give you another quick example. Another example is, in a sense, a very similar problem, but in micro-navigation, navigating through the campuses, especially for the night classes and extracurricular activities when the administration offices are closed. So as you can see, a simple design of autonomous vehicle may not be offering enough solution for these vulnerable road users to function as if they are the real stakeholders in this community and our society. Regardless, we attempt to raise some issues that we must think through to ensure fairness and accessibility of our vulnerable road users. Mobile platform for ordering to transport with both visual and the voice user interface that you saw before. Setup of the app for multiple options to suit multiple users. How they should be notified, whether it is visual or auditory, or whether it is voice command or simple alert. One question is, can we use some wearable with enhancing displays and interfaces to help the disabled to become independent? The first thing, wearables may include that are compatible with smartphones to assist and alert the disabled persons when riding autonomous vehicle using augmented reality, smart glasses with any assistive technologies. And we do know that tactile information can be so valuable, just like the keyboard spring back. So those are the useful technologies that we have to think about. The human-machine interface of the vehicle obviously is very important, specifically that the interface includes equivalent to visual and or textual method of communication. And obviously haptic technologies to help the visually impaired get access to the very much non-auditory information, very useful. But we're also paying attention to some other people around the VRUs, including caregivers, guardians, and authorities in case of emergency. Panic buttons for users in the case of suspicious activities or even accident. In emergencies, even if the rider is unconscious and incapacitated, car should be able to call 911 or even drive them autonomously to the nearest hospital. Also, the external interface to communicate with people from the outside, for instance, pedestrian. When we try to talk to each other, we make an eye contact, but how do we make eye contact with autonomous car? That's still a challenge. So there are a small set of functions that we should consider to accommodate the VRU population. Not only cognitive, there has been already mountains of studies in physical design modification to accommodate VRUs. I have just a little bit of ideas here. Ramp for wheelchair users, escalator aisle, horizontal pop-out doors. Doors can be hybrid to convert to many different cases. The speech to the clamp for safety. Object detection for auto opening of doors. Some of you already see in the commercial setting already. The vehicle design also, wheelchair restraint system to tie down a wheelchair to the vehicle. This includes a tie-down system for the wheelchair as well as safety restraint belt for the person too, of course. Steering arrangement becomes a critical issue, and optionally, some vehicles have specialized control to allow the driver with the disability to safely operate the vehicle. To close out our discussion, I just want to lay out one last thing: how administration and the restrictive legislature can cause negative impact on industries and others. The Locomotive Acts, probably you are aware of this, consistent with 3 acts. I don't have to go through all this, but the infamous Red Flag Act contained the restrictive measures on the manning and the speed of operation of road vehicles. They also formalized many important road concepts such as vehicle registration, registration plate, speed limits, maximum vehicle weight, overall structures such as bridges and things of that nature, and the organization of highway authority, which are very progressive and meaningful for the society. The most draconian restrictions and the speed limits were imposed by the 1865 Act, the Red Flag Act, which required all road locomotives, which include automobiles, to travel at a maximum of 4 miles per hour in the country and 2 miles per hour in the city, as well as requiring a man carrying a red flag to walk in front of road vehicles hauling multiple wagons. Having too much restrictions on the development of autonomous automobiles, some company basically decide to move to Germany. Now you know what happened. So I just want to impose you guys to a school of thought of what we have to do from the society perspective as well as the administrative perspective to have a very much collaborative working environment with our autonomous vehicle. That wraps up my presentation. Before we get into the final question and answer, we just want to say thank you to Dr. McBride for allowing us to conduct these wonderful research and multiple research. Also, I would like to acknowledge our partner, Dr. Justin Owens at the Center for Vulnerable Road Users at VTTI, and of course our 2 most important students, Debbie and Kelvin. Thank you, and we'll probably think we can get some questions if you have some.
Thank you, Dr. Yi and Dr. Seong. Did have a quick question for you. You mentioned that your app is being developed using, or for the Android primarily. How do you think the transition from Android to Apple might work in terms of making sure that there's more broader use or broader availability of your app for the target users?
Yeah, thank you for questions. I think you are using the Apple.
I am, yeah. Normally I'm on my laptop, which is IBM, of course, but I switched to my iPad.
Just for quick demonstrations, we have used Android development toolkits, but is Justin in the VTTI, and we are also trying to convert these iOS systems, because the iOS system has a very good LiDAR that is a part of my research. We are trying.
Okay.
We are working on it.
Yeah, I know it's pretty complex.
And any other comments and questions? Yeah, so we have recorded this presentation. Please disseminate, and whenever you have a question after replaying the webinar, then please contact us. Then we are welcome. Then give our feedback through emails or some other web meeting.